Welcome everyone. Today is day 29. What we're going to be doing is we're talking about phase changes and heating curves today. So here's kind of our agenda and what's on, just kind of the docket. First off, I need to teach you what is a phase change. What's the physical definition? What exactly happens to materials that allows for them to undergo that phase change? What's happening on a physical atomic level? And us scientists, what we do is we use something called a heating curve in order to organize and to visualize a phase change. So I'm going to teach you what a heating curve is, the parts of a heating curve, and you are going to be a master by the end of it. Now, homework-wise, you know that due at the end of this week, you have the 4 temperature conversion practice up on Canvas. It's 4 problems, just testing you on quick temperature conversions. But hint, watch your sig figs. And then assigned today, I don't have anything for you. So after you get all caught up on our videos, you do your homework, you're set for the week. Let's talk about just our learning targets for today. The first one is that, as I said, I want you really to understand what happens on an atomic level during a phase change. That you're going to be able to describe to me what exactly is happening to the atoms, what's happening to the total energy, what's happening to that material during a phase change. Then, as I said, you are going to go through and you're going to label a heating curve, including all states of matter. And finally, you are going to be able to solve for the heat of vaporization or the heat of fusion using a heating curve. And we're going to do a problem on that at the very, very end. So let's start out with just a phase change and exactly what it is. So a phase change, the definition for a phase change is really simple, actually. It's a physical change from one state of matter to another. That's it. So by itself, the definition isn't really too bad. How you go through a phase change is you either have to remove or you have to add energy in the form of heat. So imagine like an ice cube tray again. You go, you put some water in it, you put it in the freezer. The freezer is an exothermic, remember? It loses energy, and all of a sudden you get ice. That undergoes a phase change. Now, during a phase change, this is a really, really, really big idea. During the phase change itself, the temperature remains constant. So, what I mean by this is that we'll see an example in a bit, but if a material is currently undergoing a change in phase, there is going to be 0 temperature change. And then finally, the idea is that your material stays the same. If you start out with liquid water and you freeze it, you still have water, it's just in a different phase. So the chemical identity does not change. So again, just with ice, all stays the exact same. Now, let's get a little bit more into the energy. During a phase change, energy is used to spread out particles of, if I show you like a diagram between each of the specific types of phase, in a solid, your atoms are or molecules are really close together. They're in a crystalline, a set, solid structure, and they are just going and vibrating that entire time. So, what you do is during a phase change, you add energy from one to the next. So from a solid to a liquid, and now you see that the separation between those atoms and those particles are now just further apart. And when they become further apart, if you continue to add energy, then again, they spread out more and more and more, and they lose their structure, and all of a sudden you have a gas. The idea here really is talking about the energy that you're adding or you're removing from a substance is used to spread apart those particles. Instead of changing the average kinetic energy, remember the definition for average kinetic energy is the temperature. Instead of changing the temperature for these materials, you are changing the separation values in between. That is a phase change. It's only you going and pulling apart particles as opposed to increasing or decreasing the temperature. Now, you need to first know or just know some terminology. The first term that I'm going to be using a lot during this entire unit is something called latent heat. Latent heat, or anything latent heat of, means the energy necessary to undergo a phase change. So whatever you have, if you are trying to go from a gas back to a liquid, it's the latent heat of freeze or condensing. Doesn't matter. It's always latent heat. Now, let's talk about your phase changes, because you go and you think to yourself, oh, I know all of my phase changes. Yeah, something goes from this to this, it's this to... In reality, come on, there's 6 of them. The first 4, I think almost everyone knows of, or at least they've seen it at some point in time. And that is, first off, freezing, whenever a substance changes from a liquid to a solid. Melting, whenever a substance changes from a solid to a liquid. Condensing or condensation is whenever a substance changes from a gas to a liquid. And then finally, vaporization, it's not really called boiling, it's called vaporizing, is whenever a substance changes from a liquid to a gas. Now, these are, as I said, only 4. There's 6, because in reality, there's 2 more that are very, very kind of uncommon, but you need to know of. These 2 are sublimation or subliming. It's wherever a substance changes directly from a solid to a gas, much like the dry ice, the carbon dioxide here that I have shown. Or deposition, depositing, is whenever it goes straight from a gas to a solid, like frost in the morning. Any of these are phase changes, and how you visualize phase changes, I always just think of a diagram. Instead of memorizing those 6, if you understand what is happening with each, and you can tell me what the change of phase is, then you're going to be perfect. So let's do it together. If I want to go from a solid to a liquid, and I change to red to show an endothermic, I'm gaining energy, I'm warming up from a solid to a liquid. Again, if we go and look, solid to liquid is melting. So I go and I always just write melting here up at the top. From a liquid to a gas, this is vaporization or vaporizing. And then finally, our big, big, big jump, solid all the way over to a gas. This is subliming or sublimation. So sublimation. Perfect. These are the 3 whenever you gain energy. You are endothermic. So now let's go the opposite direction and let's become exothermic. So I'm going to change to blue and let's go the other direction. So gas back to a liquid. If I go from a gas to a liquid, I am condensing. So condensation. If I go from a liquid to a solid, I am freezing. And then finally, the big, big, big odd one, gas all the way over, come on arrow, to a solid. This is deposition or depositing. So I write deposition. There we go. Again, if you know this chart and you can understand each specific step from one like just phase to another, you're going to be golden. These are your main 6 and the ones that you need to know. Solid to liquid, melting, liquid to gas, vaporizing, solid to gas, sublimation or subliming. And finally, the other direction, gas to liquid, condensing, liquid to solid, freezing, and gas to solid, depositing or deposition. Okay, now let's talk about heating curves. Heating curves are really a very, very nice way to visualize phase changes. It really is. It's just a graph, and usually with the temperature on the y-axis, and then the x-axis a lot of the time could either be like time, which is what you see here, or heat, which is, again, the just variable Q in physics. Now, this is a heating curve, and we're going to go through all of the parts of the heating curve, and I got to move myself over to the side because we're going to go up here. Now, what we are going to do is that with each specific section here, so like this first part over on the side, second part, all of these have specific names. And you can see that our x-axis is the energy added as heat, so Q. Our very, very first section here is whenever our material, whatever it is always the lowest temperature and the lowest amount of energy. And you instantly should know this as a solid. This first leg of your heating curve is always, always, always going to be a solid. Then you hit this temperature right over on the side. And this temperature, again, this is a transition point now from a solid over to a liquid, and this is called your melting point. So whatever this temperature is, this line shows you the melting point, and the amount of energy in order to undergo this phase is called the heat of fusion. Okay? So you go and you have heat of fusion. After you have changed phase from a solid through the melting point, your next leg, as the temperature increases, is now going to be a liquid. And once again, at the very, very end, you are going to reach a specific temperature. It's called the boiling point. You undergo what is called the heat of vaporization. Again, that amount of energy necessary to undergo phase until finally you hit a gas. One of the things that's really, really telling about a heating curve is notice what happens to the temperature during the heat of fusion. Remember what I said. The average kinetic energy of those like particles does not change. The temperature of that material does not change during this entire portion here. During your heat of fusion, it never, ever, ever changes until you now have liquid. That is the first time in which temperature starts changing again. Think of it again this way. The energy being applied between a solid and a liquid, the heat of fusion, is being used to separate out those particles as opposed to increase or decrease that temperature. That is very, very, very important. Now, let's talk just first about latent heat of fusion. Remember, latent just means, again, how just much energy necessary you need in order to accurately change phase is the definition of latent. So heat of fusion, again, is just from a solid to a liquid or a liquid to the solid. This is always the exact same. So during melting or freezing, energy is added without change in temperature. Big idea. Vaporization is the same thing, but now it's from a liquid to a vapor or a vapor to a liquid. And I have the exact same thing. Energy is added or removed without a change in temperature. Get the idea? There is no change in temperature during a phase change. Now, finally, let's talk about the heating curve of water. This is just the original heating curve of water because water is the number one material substance that almost everyone knows. If we go and we look specifically for each section, A, again, you have solid ice. B is the heat of fusion. C is liquid water. D is the heat of vaporization. And E is just gas. Again, it's steam. So if you go through this heating curve, notice where the temperature breaks are. 0 is at the melt or freezing temperature. 100 is at the boiling point. All of these are at the exact same that you know of. Now, one thing that you may have noticed originally that I didn't really get to get into very much is this right here. This section on a graph, you know it from math. You've seen it before. This is a break. Because our heat of vaporization is so much larger than our heat of fusion, it is very, very, very common to add a break on your graph for heat of vaporization. It doesn't mess with the graph at all. It just, if you notice the numbers, it goes from 3.8 to 8 for just liquid water and then 8 to 30. For goodness sake. Like, that's a big, big value. And if you wanted to keep the same scale, this graph would be gigantic. And yeah, no, add a break. It makes it so much nicer. So finally, let's do our final problem. And our problem is, using the heating curve of water, the one that I showed you just then, what is the amount of energy in joules necessary for water to change phase from a solid to a liquid state? So here's my first part. If I'm trying to figure out the amount of energy in joules from a solid to a liquid, I want you to think solid to liquid is going to be all throughout this section. Specifically, I'm talking about B. This by itself, again, is the heat of fusion. This question is asking you to calculate for the heat of fusion for water. Okay? So our idea here is that if we want to calculate for the heat of fusion, let's first just try to figure out what our 2 points are on either side of heat of fusion. So I'm going to just go and I'm going to look and I'm going to say that this value 3.85 and 0.522 are either side of my heat of fusion. Now, this is asking from a solid to a liquid state. So if you want to think of your final and initial, my final is going to be to a liquid. This is my final. This is my initial. If I want to find and to solve for the change in heat, again, heat is Q, then I'm going to go and I'm going to solve it. What's the Q final minus the Q initial? That's what it's asking for. What's my change in heat for all of this? My Q final then is this 3.85 times 10 to the third joules. 3.85 times 10 to the third joules, and I am going to subtract out 0.522 times 10 to the third joules. This is the exact same types of problems that you will always go and figure out. So if we want to plug it in, again with our calculator, I'm going to plug in 3.85 e to the third minus 0.522 e to the third equals, and I get 3,328 joules. This is your heat of fusion for water. That means that it takes 3,328 joules exactly to change from an ice into liquid water. But that's it for the day. Thank you, everyone. I hope to hear from you soon, and have a great day. Thank you all.